talk about some applications of exponential functions, and we're going to do some exponential modeling, some exponential growth, and exponential decay. We're going to start out with an exponential growth in terms of doubling time. That's on page 371 of your book. So there's a couple things to take note of in terms of the form of this function. So the number of units in this population at time t depends on an initial amount, that's your n sub 0, or our friends across the pond will call it n naught, times 2 to the t over a. Now a is your doubling time, how long it takes before a population doubles. So let's think about something, just for a moment. If I put in the value of t was equal to a, let's think about what would happen in that exponent. I'd have 2 to the a over a. Well, a over a is 1. 2 to the 1 is just 2. So it'd be taking n sub 0, your initial population, times 2. And every time that you increase t so that it's another multiple of a, like 2a, you're going to get 2 squared here, or 4. This is going to double. So it's a nice compact model. It's not the only model that you can use for exponential growth. We'll look at other ones. But let's take a look at some of the applications here. We'll start out with a squirrel population for problem number 3. So I'm accidentally doing one of your homeworks. That's okay. Gray squirrel population was introduced into a certain county of Great Britain 30 years ago. Biologists observed that the population doubles every 30 years. The population now 100. What was the initial size of the squirrel population? Well, all right. There's a couple things to work with. Let's first of all write down the general model. N of t equals n sub 0 times 2 to the t over a. And let's think about what things we know and what things we don't know. So n sub 0, t, and a. So in terms of the things we know, well, how long does it take the population to double?
Every 6 years.
Yeah, every 6 years. So a is 6. We don't know the initial population, but we know the current population. I just called that n. I didn't put the n of t. The current population is 100,000. How long did it take to get to 100,000? 30 years. So the only thing we don't know then is the initial population. But let's fill this in and see what we can come up with. So we'll get 100,000 equals n sub 0 times 2 to the 30 over 6. Well, that's 100,000 equals n sub 0 times 2 to the 5th. And 2 to the 5th is 32. Wow, we don't even have to use any logarithms or anything fancy like this to solve. It's just a matter of dividing both sides by 32. I think a few of you are ahead of me on that one. 3,125. Yeah. Exactly. All right.
So neatly 30 years later.
Yeah, it is I guess I'd have to say I think this problem is probably contrived. I'm just going to go out on a limb on that one. Yeah, you can't get squirrels to stand still long enough to count them. We can't even get people to stand still long enough to count them. So it was in during World War II that there was a lot of different segments of the population that showed up for selective service in the military and And we realized that, oh, wow, we're undercounting a lot of different parts of our population. So they had to start changing their methods. Okay, let's see what other questions we have. It says, estimate the squirrel population 10 years from now. So let's see. I guess there's a couple ways we can do that. I mean, this is the population now, is 100,000. So I can rewrite this as n of t equals 100,000 times 2 to the t over 6. And then 10 years from now, well, I'm just going to put in a t equals 10. The other way to do that, and it'd be an equivalent way to do that, would be to use the 3,125 times 2 to the t over 6, except if I'm going to use that model, then the 10 years from now, I'm really going to be putting in a 40 here, whereas over here I'm going to be putting in a 10. Because 40 would be the 30 years from this initial population, and then 10 years beyond that. I think I like this one better. Let's do n of 10, 100,000 times 2 to the 10 over 6 power. Now we're going to run into a little bit of a problem with our answer here. This one doesn't work out so nice and neat, does it, Jeff? Yeah. So poor little Rocky got run over by a car. So for problems like this, I would strongly suggest and expect you to round it. All right. It would hurt my son's feelings to think of a little part of a squirrel. So we'll keep them to whole squirrels. Which ones?
Brunswick stew is traditionally made with squirrel. So that's
really
part of a squirrel.
Okay. How are we doing on the math part here? Now we can do another example with the doubling formula like this. There's a different way to talk about exponential growth. Now it's nice if you have the doubling time model like we did here, but sometimes you have to use a model in which they tell you the percentage by which growth occurs. And that's more of a traditional model. It looks like this. Exponential growth, relative growth rate. So instead of giving you, gee, it grows by, or it doubles every so many years, they tell you it increases by this percent. Now, does this formula look familiar here? Let me zoom in a little bit. Does that formula look familiar? It's pretty much exactly your continuous interest. Yeah, so it's the same formula. You got the same kind of things. You got an initial population. Instead of a percentage interest, you have a relative growth rate. And t is still time. So it's a pretty familiar looking formula. Let's apply it. We'll start with problem number 8. So it's observed that in a certain bacteria culture has a relative growth rate of 12% per hour. But in the presence of antibiotic, the relative growth rate is reduced to 5% per hour. The initial number of bacteria in the culture is 22. Find the projected population after 24 hours in the following conditions. So basically a 12% growth rate and a 5% growth rate. Let's just do one of those. So again, the same model, n of t equals n sub 0 e to the RT. Let's figure out what we know. N sub 0, R, T, and N. What numbers do we know out of this one for part A when we're working with a 12% growth rate? Good. 0.12 for R. Make sure that you return that to a decimal. Don't leave it as 12, otherwise you're really telling your problem that you have 1200% growth rate, which would be pretty pretty phenomenal. Also probably get out of control really, really fast. Our time was 22 hours. No, 24 hours. 24 hours. And the initial amount we had was 22. That's not a lot. After 24 hours, I think that's going to change substantially, but we'll see. So N of 24 would be 22 times e to the 0.12 times 24. And that's certainly a number for your calculator. I'm not impressed. I was expecting something much bigger. 391.91. I don't know the name because it's this Latin name. It's about 3 feet long. But there's a type of bacteria that can reproduce itself about every 8 or 9 minutes, which is astounding. Imagine making a copy of you every 8 or 9 minutes. The growth rate on that is just phenomenal. But even still, start out with, this is a classroom of about 20-some people. Start out with 22 people, and after one day have 392 people. That's a lot. That'd be a huge increase. 392. Now let's kind of do a compare and contrast with these two things. We're going to look at the two models for the same problem and see what they're like. Has anyone ever traveled to Austin, Texas? No? In Austin, Texas, they have the Congress Street Bridge, Austin, and underneath this bridge lives like thousands and thousands of bats, and they come out at night and just completely flood the sky. It's quite the spectacle. They estimate over 100,000 bats just underneath the bridge. It's just kind of funny. They're Mexican free-tail bats. It's kind of neat to watch them all come out. Now you want to go during the summer months. Probably later this month would be good because, or maybe in August, because they come out early in the drier months because there's just a lot less food around. They consume an enormous amount of insects, so they really do us some good. But let's take a look at the problem. Problem number 10. Let me get back here. So the bat population in a certain Midwestern county was 350,000 in 2012. The observed doubling time for the population is 25 years. Find an exponential model of this form for the population T years after 2012. So let me kind of zoom in a little bit on this information. We're going to actually find two exponential models. One of the form that we just did with a relative growth rate, and one of the form of a doubling time. So both of them have their advantages, and let's see those. The initial population is 350,000, and the doubling time is 25 years. So the first one shouldn't be too bad. Let's see if we can't figure that one out. So this is problem number 10. N of t is going to be n sub 0 times 2 to the t over a. So for part A, well, n sub 0, that's your initial population, 350,000, times 2 to the t over a. The doubling time is 25 years. So great. Got the first part. The second one is going to require a little bit of work. And actually, for the first time, we're actually going to have to do some work with logarithms, because we're trying to find an exponential model for the population. Now, let me see if there's a little bit of a hint here for us. No, it's not. Okay. So part B, we want a model of this form. N of t equals n sub 0 e to the rt. Well, they didn't really give us r. So that's where you're going to have to do some work here, is to figure out what r is. We do know a little bit, and that is that the doubling time is 25 years. So let's think about this a little bit. N sub 0 is 350,000. T is 25. N and R. Well, I claim that we kind of know N here. If the doubling time is 25 years, if I put 25 into this formula, what should I end up with? Yeah, 700,000. And R is unknown. We have to figure out what R is. But this is now a good exponential equation. Let's fill in everything here. 700,000 equals 350,000 e to the 25 times R. Because it's double this. Because after 25 years, the population is going to double. Yeah, 1 second. Okay, so after 25 years, the population doubles, so we're going to end up with 700,000. I need to solve for R. Suggestions. What can we do to solve for R? What would be a good first step? I think before I start trotting out the log, I would divide both sides by the 350,000. Yeah, 2 equals e to the 25r. That looks a little bit easier to deal with. I'm liking it. In fact, I want to point out something that we're going to use later. Did it really matter what we started out with? 350,000 and ended up with 700,000? We could have started out with 6 and ended up with 12, right? You could have started out with a sub 0 and ended up with 2a sub 0. It really didn't matter exactly what we started out with. What matters is that we ended up with double what we started out with. All right, let's keep going. Now I think some of the ideas you were giving me are going to be helpful. What next? ln of both sides. Now usually I do log base e. I just, in a hurry, I wrote down ln. But that's okay. We still get the same simplification on that right-hand side. So what's the right-hand side then? 25r equals the ln of 2. Yeah, divide by 25. ln of 2 divided by 25 equals r.
So why doesn't because you have an exponent 25r, why does it go down to the number 25r instead of making it 1 to the 25r?
Well, what's happening here is that this is really log base e of e to the 25r. And these two things cancel each other out. So all you're going to get is the exponent. So it's just 25r. Now, ln of 2 divided by 25.
Is roughly 0.027.
Thank you. So about 0.2 or 0277, etc. And that's R. So that's your relative percent growth rate. On average, this population is growing a little bit less than 3% per year, about 2.8%, roughly. Our model then is this. It's going to be N of T equals 350,000 e to the 0.02772 times T. So the advantage of this one is you can look at this and say, okay, this is the relative percent growth rate. The advantage of the other one is you can look at it and say, oh, I know how long it takes it to double. But you can go from one to the other without too much of a problem. So, before I move on to part D, are we okay with part B here?
What's the difference between ln and log?
Well, ln is really taking the place of log base E. It's a special case of the log. It's the case of the log when the base is E. So we could have all kinds of different bases. We worked with some earlier today. We had base 4, etc., base 3. But when it's base E, we call it the natural log, and we just use ln. All right. Thanks for the question. Let's finish this up then. Part D asks us to figure out how long it'll take the population to reach 2 million. So I guess my question to you is, which one of these models do you want to use? Do you want to use this one, or do you want to use this one? The one from part A or from the one from part B? Either way, we have to figure out when the population gets up to 1 million. Okay, part B then. Good choice. All right. So let's copy down our model. This is part D. We've got N of T equals 350,000 e to the 0.02772 times T. That's a 7 in there. So if I want to know when there's going to be 1 million in our population, then let's put in 1 million for N of T. Was it 2 million? Okay, thank you. 2 million. E to the 0.02772 T. So go ahead, solve. Solve for T. Solving for T here should be pretty much like solving for R in part B. Divide both sides, take logs, divide again. answer that'll happen within a reasonably long lifetime from now. Yes. That shouldn't. Okay. You got to divide after you get the log of that, then you divide. All right, let's see. Still got sound. Okay, good. All right, so kind of like the previous one, part B, we're going to divide both sides by 350,000. So on the right-hand side, you're just left with e to the 0.02772 times t. On the left-hand side, let's do ourselves a little bit of a favor and cancel out a bunch of zeros. So you're really left with 200 divided by 35. Why not? Yeah, it's a a couple like, oh really? Go think about it. What you're doing when you cancel out a zero, you're dividing both the numerator and denominator by 10. So I just made my life a little bit easier. Yeah, you'll still get the same. It was about 5.7 something, I think. Let's check. So 200 divided by 35. Yeah, 5.7. Okay, so 5.7. Now what? Now I want to take the log on both sides, right? So ln of 200 divided by 35 equals the ln of e to the 0.02772 t. Then the right-hand side becomes 0.02772 t. I'll just leave this as it is, 200, like that. So I want to take the log of that and divide it by this. So the ln of 200 divided by 35 divided by 0.02772 equals t. Now I'll show you a couple ways to do that on your calculator. One is you can just do it all together. You can just do ln of 200 divided by 35, right parenthesis. You need to close off that log with a parenthesis, divided by 0.02772. And that's one way. Another way, if you're kind of working your way through and getting numbers all along, you can do this. Let's take 200 divided by 35, and I get an answer. Then what did I want to do? I wanted to take the log of that answer. So hit the ln key, and then the second key, and then this, right here, the opposite key. And that'll put in your previous answer. So you're taking the log of that number. Then what I wanted to do, I wanted to divide this number, I wanted to divide that by 0.02772. So if you hit the divide key, it automatically puts your previous answer there divided by 0.02772. So, same thing. Whatever you're comfortable with, just find something that works for you on your calculator. 62.87, call it about 62.9 years. I don't think this would be that accurate that we could round anything more. We should probably round to the nearest year. How are we looking on that one? Okay. Let's see. Let's look at radioactive decay. Problem number 18. Says the half-life of cesium-137 is 30 years. Suppose we have a 10-gram sample. Find the function that models it. So we're going to be doing two different models, kind of like we did with problem number 10. So cesium-137, I think that's Ce-137, has a half-life of 30 years. This is the stuff that would be left over after being used in a nuclear reactor. Now, we want to find a model of this form. M of T equals M sub 0 times 2 to the negative of T over H. T over H. H is your half-life. So that's given to you. H is 30 years. M sub 0 is your initial amount. So that's 10. So I could rewrite this for this problem as 10 times 2 to the negative T over 30. So there's this book that I have on audiobook, and it's kind of whimsical. It's called What If? And they ask all kinds of crazy questions like, what if everybody on Earth took a laser light pen and shined it towards the moon? Would you see it? And the answer is disappointing. No. But then they amp it up. They're like, all right, so let's take the brightest light on Earth, which is at the top of the Luxor Hotel in Las Vegas. And if everybody had one of those, then what would happen? And they keep on amping it up, and it's kind of fun. One of the comments though was after if all humanity died, what would be the last light left on Earth? And it would be the Cherenkov radiation that comes from the leftover spent cesium from all our nuclear reactors. And there's this dim glow. After 200 years, it'd be a little dim glow of light left over. So maybe we can play with this model after a little bit and see what it says. But for right now, part A, I think we're done. We just got it. It's 10 times 2 to the negative T over 30. So if T was equal to 30, I'd have 2 to the negative first power, which is 1/2. Basically, you'd be multiplying the 10 by 1/2. You'd decrease your original amount by 1/2. So part A is done. Let's take a look at part B. This is function M of T. Find a function M of T that models the mass remaining after T years. So M of T in this case, they want us to write it as M sub 0 E to the negative RT. So this is kind of like the part B from our previous problem. Well, let's think about what we know. Well, we don't know what M is. We do know what, we don't even know what M sub 0 is. We don't know what R is. We know that T is, what, 30 years? Yeah, actually M sub 0 is 10. All right, good. M sub 0 is 10. Now, after 30 years, what would M be? M would be 5. So let's put that in and see if we can't solve for R in our model. So we have 5 equals 10 e to the negative R times 30. And now we're going to try and solve that equation for R. You should be dividing both sides by 10. We'll get 0.5 equals e to the negative, I'm going to rewrite that as negative 30r. What do I do from there? ln on both sides. Good, thank you. So ln of 0.5 equals ln of e to the negative 30r. So ln of 0.5 is negative 30r. Divide both sides by negative 30, and you should get a value for r like this. So negative ln of 0.5 divided by 30. I'm getting it about 0.23. Is that roughly what you guys are getting for R? Are you able to match that calculation? So I've done a couple examples now. Part B here in problem number 18 and part B in problem number 10 where you had to find this constant, that R. Are you comfortable with those calculations? I don't see anyone nodding no. Cooper. Good question. So after 30 years is the half-life. So half of 10 is what you're going to end up with after the 30 years. So that's where we got the 5. Other thoughts on problem number 18b here? So our final model is going to look like this. M of t is going to be 10 times e to the negative 0.0231 times t. And that's an equivalent model if you were to graph this function at the same time you graphed this one up here, you'd see you get the same thing. They'd represent the same graph. Because the original model had a negative in it. So, yeah. And if I forgot, if say I was writing down the problem and I just wrote down e to the RT, then after our calculations, you'd end up with a negative value for R. So you'd end that it had that same value either way. Okay, last one here for the section. There's really a couple more that I'd like to do. I'm only going to do one. And that is radiocarbon dating. Problem number 24. Now, I'm not going to make us take the time to solve for R in radiocarbon dating. You could You should check it. In fact, here's a little homework problem for you. Check that for carbon-14 with a half-life of 5,730 years, the value of R in this model, m of t is m sub 0 e to the RT is, in fact, I'll leave off the negative here, but it's going to be R equals negative 0.000121. All right, but for the sake of this problem, let's start out with that. I want to get through this one quickly and finish up the section. So m equals m sub 0 e to the negative 0.000121 t. This models the exponential decay of carbon-14. It's a radioactive isotope of carbon. Carbon usually, I think, has 12 neutrons. This one has 14. So they ask us, or the problem says, the burial cloth of an Egyptian mummy is estimated to contain 59% of the carbon-14 it contained originally. How long ago was the mummy buried? They're not giving us a whole lot here, are they? Let's take a look at our variables, m sub 0, and t. There's a little bit of a trick here that I've kind of hinted at a couple times. We don't know what m sub 0 is. Could have started out with any initial amount. We don't exactly need to know that because we ended up with 59% of the original amount. And t is our unknown. But 59% of our original amount. We can actually put something here. We'll start with the decimal value for 59%. That's going to be 0.59. What does the word of translate to mathematically? It's actually going to be at times. The original amount. What can I put in for the original amount? M sub 0. That's what this is. It's the original amount. So how does that help me out? Well, here it goes. That's going to be in for m. So I'll get 0.59 m sub 0 equals m sub 0 e to the negative 0.000121 t. Exactly. So if your head is spinning at this point, you're going, oh, I don't get this. How are we going to solve? Well, you can divide both sides by m sub 0. And you get 0.59 equals e to the negative 0.000121 t. So I hinted at this with our bat problem earlier. When we started out with 350,000, ended up with twice that. I said it really doesn't matter what you started out with. You just know, relatively speaking, what you ended up with. Here we start out with m sub 0. We ended up with 59% of m sub 0. So you're just left with 0.59 equals e to the negative 0.000121 t. All right, let's finish solving here. ln of 0.59 equals ln of this. ln of 0.59 is negative 0.000121 t. What's the last step? Divide. And let's see how old that is. Now, carbon dating has a lot of problems. It's not as nearly as accurate as we might like, in part because of all the nuclear testing we've done throughout the years. I think they recognize that there's probably at least a 3% error in those dates, but it's just pretty good. So I'm getting about 4,360 years, 61 years. Should probably round it to 4,400, because like I said, I don't think it's that accurate. But I'm more worried about the math than I am about the accuracy of carbon-14 dating. They gave it to you in the problem. It's oh, I mean this one. Oh yeah, you'd have to figure that out. The way you would figure that out is you're going to use this model, and what's going to happen to the initial amount after 5,730 years? It'd be half. So another problem that you could solve would be 1/2 m sub 0 equals m sub 0 e to the r times 5,730. So solving that will show you how you get r. Because just like the one we just did, the m sub zeros are going to cancel. So there's an extra step in this problem beyond what I gave you. Let me recap a little bit. Let's start out with the model right here. The important thing to realize is they tell you that you end up with 59% of the original amount. So if your original amount was m sub 0, you've got 0.59 m sub 0. And that's the part that makes this whole problem work. Because if I can put in this on the left-hand side of the equation, then my m sub 0's can cancel. And then I can solve. Yep. For homework, this is section 4.6. For homework, try 1 through 11, 17 A through C, and for problem 23, you can use the formula that we just did. Use A equals A sub 0 e to the negative 0.000121 t. And I don't know why I wrote down A sub 0 here. We've been using m sub 0, but same thing. Same model. This is the formula for the decay of carbon-14. I have to give you something. Now, what I probably wouldn't do, because it becomes too long of a problem, is make you do both things. Problem 24 asked you to do both things. It just told you that the half-life was 5,730. From there, you need to figure out what r is by solving here. That gives you this equation. Then you need to solve another equation. So that's really solving this twice. And there's two things. One, it makes it a really long problem. And two, if you make a mistake on one part, you're going to get the second part wrong. So I would only give you one part of that problem. Either that's the half-life, figure out r, or here's the model, figure out t. So one of those two parts. Let's take a break.